Welcome back. I'm very delighted to introduce our distinguished keynote speaker, Ilja Kuzborskij from Google DeepMind. So Ilja did his PhD in EPFL in Lausanne back in 2018, and after that now has been working for years already in Google DeepMind, in a group that primarily focuses on theory side, but Ilja will tell you more. And he's been working on LLMs and uncertainty, among other things. So his talk is about to believe or not to believe your LLM, a topic that is really important these days, as we all know. And I'm really particularly happy that, I find it's really important that there is a nice bridge between academia and industry. And groups like where Ilja is working, I think, are really important for all of us to make that bridge happen better. So they publish work and they come to speak, and so that it's more connection between academia and industry. So without further ado, I'm really happy to introduce Ilja, and the floor is yours. Thank you. And you have full hour still. We're starting late, but yeah.
Thank you so much, Melis, for introduction. Thanks for organizers for being wonderful hosts. Yeah, I'm very happy to be here. I heard the many interesting works, both in theory and from applied side, very inspiring. So yeah, this is going to be about uncertainty, more a little bit on the theory side, but not too much. Really, the motivation behind this work was, I guess, to come up with some metric of uncertainty, which is reasonable from a rigorous point of view, from the rigorous analysis, and at the same time something that can be estimated in practice. This is a joint work with my great collaborators, with Yasin, Andras, and Csaba, and Csaba is leading the team. All right, let's go into it. Just a very brief recap on what language models are and the cartoon and in the cartoonish representation. So we can think we can think of them as a variable length Markov models. So sorry, given some prompt, there are several possibilities in this probabilistic model. If we sample from it, what can it generate, and then based on this response, there is some other potential answer, and so this Markov process branches out on and on and on, and that's a cartoon representation of how the language modeling works from a probabilistic viewpoint. And this is a variable length Markov model because some of the words or tokens that appeared early on might be important, and some just preceding ones might be important for the current answer, for the current next generated tokens. So this is basically also to set up some notation. Prompt is going to be X. It's always going to be fixed. It's not a random variable here. And of course, as you might know, sampling happens token by token, which is roughly equivalent to a word. So first, at the very beginning, given the prompt, we sample first token or first word, and then we put this token back into the context, and then so on and so forth. We go, and then in this way, we generate capital Y, which is going to be a piece of text, or simply a tuple of tokens. And more formally, if you want to think about this, then the prompts and the texts are going to belong to the space of strings, this calligraphic X. And then we are interested in studying these conditional distributions, family of conditional distributions. And the P is going to be the language, ground truth. It's a probabilistic modeling assumption here. And the empirical language model is the way we actually try to learn the ground truth is the language model, right? And then whenever you see this notation, it means that we independently sample many responses to the same query, which is X here, right? Now again, so far I only spoke about setup. I didn't speak about neural networks. Nothing. It's a pretty much on the abstract level, but just to have some basic foundation of how we learn, or how the pre-training phase in these neural networks or these language models work. This is basically boils down to minimization of what is called log loss in statistical learning, or you can think of it as a maximum likelihood or log likelihood over a family of these language modelers. And of course, here it's written in the most general way because I'm minimizing my log loss over strings. But as we know, in practice, this happens token by token. It's a next token prediction problem. But thanks to the chain rule of the probability, this factorizes, and what people in practice do in practice, they try to predict the next token given available ones. But in the context of this talk, it will be valuable to think about the entire generations, or the modeling or learning on where one example is the entire piece of text, or the example, or the entire string. Sorry, this is this Y's, right? And then the goal, although it's not always explicitly stated in these papers, but the goal is to minimize really the scale divergence, or the in statistics what is called excess risk. And excess risk is between if you think about it, is the expected log loss of the language model and the expected log loss of the language itself, or the entropy of the language. And so very often, if you look at the papers that speak about scaling laws and whatnot, they are somehow modeling this quantity trying to model this quantity in the empirical way by curve fitting, and this is always irreducible component that we want to achieve is the entropy of the language, right? In modeling of the language. Now this talk is going to be about hallucinations, right? Or the loosely speaking, about incorrect answers to a given query. I will not focus here on reasoning or something. I will just focus on a simple one-shot answering language models. But I think all of this setup and formalism is still applicable to reasoning models. If you think, for example, that this Y is a collection of all reasoning trace and the final answer, or all together, right? So this Y, or the answer, is distributed according to the joint distribution of a language model, right? So it's not, it's not one token at a time. It's a joint distribution. So we think of it in this way here, right? And of course, since it's a density estimation task, inevitably we will, in this density estimation tasks, we will underestimate some low density regions in the language, in the ground truth. And maybe we put a lot of mass in those, during modeling, during training, we put a lot of mass in those regions. And so occasionally we sample from this mass, from these regions with a lot of mass, and loosely speaking, this is where hallucinations come up from, right? At least in the context of this talk. And clearly one can say this is because of lack of training data or maybe the right specification of the family of models in which we train. But going further, I will try to associate hallucinations with uncertainty. And here, if we delve even deeper into into what it means in the context of question answering, let's say epistemic and aleatoric uncertainty. I mean, I'm preaching to the choir, of course, but I will narrow it down what it exactly means in the context of this talk. And epistemic uncertainty will be lack of the ground truth, lack of the knowledge about ground truth. So we remember that we want to recover P, or the ground truth, and that's insufficient data, or maybe insufficient knowledge about the model class, right? We, for example, over-specify or under-specify our model class. And aleatoric uncertainty is some irreducible randomness which is always present in the language. For example, there are multiple answers to some of the questions. Let's say one example of the epistemic is are the facts which only have one answer, and these are well-known facts, like what's the capital of some country. And the example of the aleatoric uncertainty is name a city or a fruit, or you know, and that's not necessarily restricted to a single answer. Of course, we might very often think of this in some equivalence class. Let's say if I ask for a proof of the theorem, there might be many different proofs, but are somehow equivalent in terms of the idea. But I will not go into this kind of details. So we want to distinguish between these two, and we want to understand when the epistemic uncertainty is high, or the aleatoric uncertainty is high, but we want to do it without access to the ground truth. So the assumption, and it's a very practical assumption, that we cannot sample more data or from the environment, from people or textbooks or whatnot, but at the same time we can obtain responses as many times as we want from the language model, and we can obtain log likelihoods of these responses. And so the goal will be to estimate some sort of quantity, which I will speak about, some sort of divergence between these two conditional probabilities, right? Recall that P is the ground truth, Q is is a language model, right? And we want to do it in some way, either give an upper bound or lower bound, and this will serve different purposes in a way that it can be computed. It can be computed from data, and we can use it in practice, of course. So LLMs are complex. Complex neural nets, and they're ever evolving. So we also want to abstain from making a lot of structural assumptions about these models. The only possibility that we will have is access to the sample. Can we look at them in a black box way and exploit their autoregressive nature? And at this point, I want to show some quick experiment that led to a lot of content here. And the experiment is the following: we ask some question to the language model, but then, given the answer, we also keep adding a lot of incorrect answers. this is not what the final result will be based on. This is just a proof of concept, like experimentation, if you will, of stability of language model to erroneous answers or perturbations in some sense. And interesting observation, sorry, there is some sort of glitch. So an interesting observation is that if intuitively a question is some very well-known one for which you have a lot of data, then even with a large number of incorrectly added answers, it's really difficult to sway a probability of a correct answer to be small, right? And these are examples. Close to 1. And so if you have some more specific answer for which there might not have been a lot of training data, and this, I believe, is a small language model. It was done also several years ago. For example, who's the author of The Grapes of Wrath? And then you answer it, you insert a lot of Hemingways in the context, and you quickly see that this breaks down, and the probability of correct answer simply decreasing, right? And this is interesting because it seems that language models are convincible, but convincible not in the same way. The same is with here are some other examples. The same picture. And for multiple response queries, we see some sort of a similar picture, but the drop is not as dramatic because, of course, there are several possibilities, right? But at this point, perhaps we can capitalize on this and develop some sort of intuition or metric of how things of how to capture both sources of uncertainty, if it's like epistemic, or if it's epistemic or aleatoric, if it's a single answer queries or multiple answer queries. The behavior of the language model seems to be similar when they don't really know that well, and it's easy to convince them. And so, again, in practice, we don't necessarily have access to incorrect answers, but the intuition somehow, is that maybe once we keep querying the language model, once in a while, they answer things incorrectly. And these incorrect answers and correct answers can be placed back into the prompt. And so we have this bootstrapping process, not in a statistical sense, but bootstrapping in a sense that we are bootstrapping incorrect answers and increasing probability of language model answering incorrectly. But that's of course very high-level intuition, which I will formalize. But of course, so far our requirements is that it's a black box success. We don't have access to the ground truth. So in general, from computational and statistical viewpoint, it's impossible to do anything in this case. But one assumption we will make, and this is assumption about the language, and in particular is that the language should not be sensitive to distracting information. In other words, if I ask some question, and then multiple times, or maybe once, I answer something correctly and then incorrectly, and so on and so forth, then I will want language to be still answering the correct thing. Probability of the correct thing should be the same. So the language itself, or the ground truth, should not exhibit this property that we saw in these experiments. Right, not sensitive to distracting information. And this, so far I spoke a lot about this, about joint distributions and the text and the answers and whatnot, but how is this done in practice? What's the connection with the language models? Well, we can think of construction of this joint distributions through it as an iterative prompting process, right? If I want a sample from a joint distribution, what I can do, given an initial query, I receive response, and then glue it together with in some way with the prompt. I have a concatenation, I ask LLM again, I receive response, and so on and so forth, and I add these responses into the prompt, and this you might see as this iterative prompting. On the other hand, from the probabilistic viewpoint, I have this decomposition arising. So I'm progressively sampling these texts, and so I'm constructing in this way joint distribution of responses given a query. Right? It's not exactly chain rule; it's a pseudo chain rule because I have these f functions which represent prompt, or how do I arrange these answers, these responses into a prompt. But all the theory it also works out for the pseudo joint distributions that arise from this pseudo joint chain rule. Right? In a little bit more formal way, and the example here is that here is the example of this template function. Consider a question. Here is one answer. Then here is another answer which we received in the iterative prompting, and so on and so forth. Right? And this can grow, and this can grow and grow and grow. And of course, given we again have this pseudo chain rule, and so in this way we can obtain a sample or a tuple of these responses given a query. So far we modeled the pseudo joint distribution of the language model. In the same way, we can think about the language, right? P is the ground truth, and the Q tilde is the pseudo joint distribution of the language. And here comes the assumption which says that something about insensitivity to distracting information. So if P is the ground truth, then no matter which kind of answers I place into the prompt, the probability of the correct answer should still be preserved. I mean, it's very intuitive, and if it makes sense, if I ask you what's the capital of UK, and then I say a million times London, and I say once London and place million times Paris into the prompt, the language would still respond London. So this assumption is fairly reasonable. So under this assumption, you can prove the following. It's really somewhat standard result. If you think about it, it's a bit of information theory and Jensen's inequality at some point, but extended to these pseudo distributions, right? Because of presence of the f function. And what it says is that the KL divergence between the joint distribution of the language model and the joint distribution of the ground truth can be lower bounded by the mutual information between all these variables, between all these, or the mutual information of the joint distribution. Sometimes this is called total correlation in statistics. Right, here is the definition. Mutual information in this generalized sense is a KL divergence between joint and the product distribution. So it's exactly that. So if you think about this, this, in some sense, this lower bound tells us about independence, right? So if I assumed independence, if I assumed independence of responses in the ground truth or in P tilde, then any distribution that does not obey independence cannot be close in the KL divergent sense to the ground truth. And this cannot be closeness, it's captured by the mutual information, or how independent these random variables, which are responses, are, right? From one point of view, it's already interesting and potentially useful, because one can think, well, given a response, I can try to estimate what's the will I suffer high hallucination, or will I be far from the language truth, from the language, from the ground truth, or from the true model of the language. But I can only say when I'm far, but I can never say when this is small. I don't have an upper bound, so I cannot say when the uncertainty is small. And for some applications, this is already useful, for some not. For example, if I want to do some sort of exploration, I would need an upper bound. I would need to know what to explore. But for hallucination detection, for example, if I have a lot of queries and I want to understand whether I have sufficient training data for those, I can totally rely on estimation of this lower bound. Now, you might of course say that, well, it's interesting in theory, but this estimation of mutual information is crazy hard, especially when you have a joint distribution over multiple texts, and each of the texts is composed of multiple symbols, and each symbol is in a huge alphabet. In general, this is of course true, right? In general, this is true, but we're not dealing with all possible general cases. We are dealing with the language, and in the language there is a lot of Zipfian structure, right? There is a very quickly decaying densities of words and of sentences, and their equivalents are typically quickly decaying. And so maybe it's not so hopeless. I will get back to that a little bit later. And so here's the intuition also behind the KL divergence, like a graphical cartoon. Why KL divergence in this case makes sense. So if this would be our ground truth, and this is on the x-axis we have space of the joint responses, right? And if the ground truth places some little mass in some region of the joint responses, then if our language model suddenly has a lot of mass in that region, KL divergence is going to be high, right? And this is precisely what we are capturing through the lower bound, right? Again, lower bound is of this form. Okay, so just a few additional additional comments is that this quantity is not the same as the excess risk I showed at the very beginning, and what people try to estimate in scaling laws and whatnot, because these terms are flipped, right? But the estimation of this quantity is much harder, because to give bounds on this, we would need to make much more structural assumptions about about models, about neural networks, about approximation error of this language, and so on and so forth. So this quantity is easier to study, but I suspect that getting an upper bound on this is also non-trivial, because it will have all the same bags of problems as dealing with this quantity. So lower bound here is something that we could do, and something that it turns out to be insightful and useful. So about usefulness, here I just present. It's really basic mutual information estimator. So the pseudocode is adapted to this particular setting where we have multiple texts. So the important, there are two messages here. The estimation works essentially on constructing empirical distributions, which is horrible in general, because you would need to compare different sentences or like tuples of sentences. But in practice, this can be replaced by some semantic equivalences. For example, instead of comparing sentences, you compare embeddings in a language model, and then the space of sentences immediately shrinks dramatically, right? That's one thing, and another thing is that correct estimation of this mutual information requires not only generating each of the texts, which, remember, we generate by iterative prompting, right? But also obtaining a case sample of those. So it's not if iterative prompting, but also doing iterative prompting, repeating iterative prompting independently k times. So if one has to do it with the statistical guarantees and some statistical quality, then it's very expensive procedure, right? Estimation. Right. This is what I just said about the some notes on the estimation, and this estimator indeed. What I said before about Zipfian, about this mutual information estimation and Zipfian setting, this estimator is not doomed, because one can show this lower bound on the mutual information in terms of this estimator, of the estimator produced of this estimator, right? K is the sample size that we had in the algorithm, and alpha here is going to be the power that we see in the Zipfian distribution. So basically what it says, the larger is the alpha, or the steeper is the decay in the Zipfian distribution, the faster will be the rate of convergence of the empirical mutual information here to the mutual information. And you can see that for alpha equal to 2, we essentially recover parametric rate, right? It's going to be 1 over square root of k, which is a parametric rate in statistics. And this is something remarkable. This is just a slight improvement of this result for effective support. But yeah, so the bottom line here is that estimation is not doomed. Mutual information estimation, or the estimation of the lower bound in that theorem is not doomed once we assume that we're dealing with the quantities, or with the random quantities which are Zipfian, right? Zipfian distributed. And here's an example. It's a quick experiment that we run on the on some question answering benchmark, trivia QA. I guess by modern standards, it's very, very simple, but this was several years ago, and with much weaker language models than we have now. But the point here is that so this plot somehow shows the frequency of responses. Of responses per or diversity of responses per different queries. And you can see that most of the responses get essentially, most of the queries get essentially the same responses. And then responses which are sufficiently diverse are decaying really rapidly off. So we are effectively dealing with the spaces of responses which have effectively small support. So it's very, the indication is that it's very likely that everything is Zipfian here, even in language models. Right, so as I said before, application is hallucination detection. How would you do that? Well, remember we have this bound. One can use an empirical estimator to estimate this quantity up to some rate, which is hopefully is decaying quickly in the sample size. And the next thing is in detection is of course calibration, right? So having this quantity and some holdout sample, one can just essentially learn at a threshold which would tell that whether it's a hallucination or not, or it's like training a really classifier, a binary classifier. Now, we had a theorem before. We saw this theorem before, but now a couple of words on intuition. There will be no proofs here. Why iterative prompting, as it happens here, work. This is the picture we saw before. Is just a recap for some difficult questions. It's possible to sway language model to answer incorrectly just in few responses, and this is pretty remarkable. And if we go inside of the language model, try to understand it a little bit from the mechanics of neural network involved. Well, these are just hypotheses. There will be no proofs. These are based on transformer architecture, and the key in transformer architecture, I will just skip this text and show the picture. I think it's just easier. The core of the layer in a transformer architecture is a so-called attention mechanism, or you have parameters. You have parameters which are W's here, and V and V in here, and Z is the input, typically embedded in some high-dimensional space. Once you compute that, and that's somehow end-of-line vector, typically. Once you compute that, you obtain attention weights by applying a softmax, or in other words, this layer picks up some important bits in the context, but context is now the input to this layer is represented now as a collection of these embeddings of words. And so we identified two regimes here. Remember that before we could see that for some queries it was virtually impossible to sway language model to answer incorrectly, but for some it was very easy. So in the case where we suspect that in the case where it's virtually impossible, the embedding of the query is pretty much aligned in among the principal components of this parameter matrix, or what is called in the language model terminology as a product of the query and the key matrices. And so the softmax in this case will be very close to a Dirac on one thing, right? On one element in the context. And so then we will respond something which is which was present in the training set, because this is the pattern of the softmax responses that the neural network saw a lot of time during training. But however, if the query is such that the input is not known, so it approximately lies in the null space of this query key matrix product, and at the same time we added a lot of things in the context. Then the softmax scores are going to be very close to the uniform distribution. And so at this point, language model will pick up response pretty much at random. Of course, conditionally somehow on whatever is available in the context. This is more like formal. It's the same as in the previous slide, but with some more equations. So that's the self-attention layer, and Z is the input, and M and WV are the trainable parameters, right? Right. So, right, and these two examples that I just showed are more formally represented in this way. So in one case, we really pick up the vector which corresponds to the correct input, because softmax is very close to a one-hot distribution, right? And in another case, it's close to the uniform, and we pick whatever appears very often in the context. So in that case, it was Y. Some other response which is probably incorrect. Right, this is the same. So yes, these are conclusions. So I'm close. I'm pretty much done here. So this is to recap. Here we try to propose a mechanism to say something more or less formal about the. I mean, more or less in within the constraints of what is of the assumptions. About the gap between the language model and the ground truth, and it's really remarkable that you can say something, at least in terms of the lower bound, without having access to the ground truth and without making further assumptions. In fact, the same should apply to any autoregressive mechanism, not only limited to any autoregressive process, not only limited to language models. However, this only can tell us when uncertainty is low. It doesn't tell us anything when it's high. For example, in RL applications or in bandits, we might want to know which queries or which actions result in high degree of uncertainty, so that we explore these actions more. And of course, the estimation of mutual information here is pretty expensive. We need to run iterative prompting for each query, and not only that, and to have some statistical guarantee, we need also to have a large sample size of these things run in parallel, of these prompts run, iterative prompts run in parallel. Of course, on the other hand, this all assumes that we have access to log likelihoods or to probabilities of responses. If that is not available, then the problem becomes even harder, because now you need to construct estimates based on some sort of estimates, for example, empirical distributions, whatnot, by just querying these language models many times more, right? And that's it. Thank you.
Questions?
It works. So, first of all, thanks a lot for your talk and an interesting way of looking at things. I'm trying to interpret the theorem you were showing. Mm-hmm. So, if like the mutual information will be high if they iteratively generate different responses from the language model, are the same, if they contain the same information, so if they do not change. And so that means the model is reliable.
No, it's going to be zero, right? If it's very sure in something.
Okay, then it's zero, and okay, so the
Yes.
lower bound is very low.
It's not informative, right? For that, you would need an upper bound to say if it's.
Right. So I'm trying to understand the implications of this. So does this only apply to iteratively drawn prompts, so the second given the first, third given the, like you continuously, repeatedly ask it, not independently? Because in the end, in practice, of course, we're most interested in estimating the certainty or uncertainty or reliability of a single response. We just ask the model once and we want it to give us a good response, or we want to know when we shouldn't trust it. Yeah. So if we take one particular case of the theorem where this number of big Y's is 1.
No,
does that tell us anything?
No, in that case, it will not be interesting, right? Because if you think about this, I mean, it will not give us anything meaningful. Because in this case, you can see that this is the divergence between conditional distributions. So we can only say something about how different conditional distributions are. Right. So in some sense, if you translate it into, if you think about uncertainty, it tells us about something about uncertainty of the query, not about uncertainty of the response. And indeed, like given that unless temperature is 0, of course, in these language models, if you draw, it's a probabilistic model, so you cannot really conclude anything based on just one sample. You need to have a sufficient statistic to say something about the entire model, right?
Okay, I think I understood it. I was thinking in terms of which conclusions can we draw from the iterative prompting about non-iterative prompting, but as you just said, so it's not about estimating the response reliability, but rather the confidence of the model when reacting to a certain prompt. So it's about the estimating the prompt.
Right.
Okay.
But like, suppose you have really infinite compute, and the user comes up with the prompt. You run iterative prompting, collect many samples, whatnot, and then the system can say that, well, mutual information is high. In that case, maybe it's better to abstain and not reply anything, because this is the query which was probably not covered by the training data, whatnot. We don't know exactly the reason why, right?
And if it is low, the best you can say is you should not distrust the model.
Right. So to have a complete picture, we would need an upper bound, right? Which is the most interesting case, but it's much harder to obtain one.
Yep. Okay. Thanks again.
Can you maybe perhaps? You had the pseudocode, but maybe for people to understand, make it easier to understand, like, when do you get actually this mutual information to be high? Like, what do you see in the samples through that iterative prompting? If a practitioner runs, what does the data look like so that mutual information would be high?
When responses are sufficiently diverse, right? But at the same time, diversity. It's essentially that.
Diverse. So basically, you run your prompt first, just the prompt itself, and then you start iteratively add the previous answers to the end of the prompt, and
there is a nuance. So diversity is not an only thing, because in that case we would just look at the entropy and we would be done. Let's say, right? And indeed, semantic entropy is another popular. Just computing entropy is a popular way of doing things. But maybe we want to. We still have diversity, but the aleatoric uncertainty is low, right? Which means that we have diverse responses by nature, right? And that's the point really of having mutual information, because in that case, mutual information will be low as well, because remember that mutual information is the scale divergence between joint and product distributions. So even if we have diverse responses, these two can be close, right? Because we're sampling from the joint distribution, which naturally have different responses.
Hello, thank you for your nice presentation. My question is about the fact that you assume that the responses are independent. Have you considered a case where they are dependent or sequential, like in a, for example, chain of thought situation?
I mean, in that case, the simplest way to approach this is just to clump everything together and say that entire chain of thought is a response, right? But I mean, I can have a bunch of independent chain of thoughts, right? That's the simplest way to address it. Of course, on the other hand, what happens is that you blow up the size of the support. So potentially mutual information estimation becomes harder. But in practice, I think people anyway rely on embedding vectors. So maybe I mean nobody does I think estimation of some through constructing empirical probabilities on top of vocabularies. It would be crazy hard, right?
Yeah.
So.
Thank you.
More questions?
Yeah, maybe I'll ask a question as well. This excessive risk looks a little bit familiar, like similar to regret. Regret being basically taking an action under predictive distribution, basically compared to, in hindsight, if we had taken the optimal action, what it would have been like if we had taken actions according to an oracle. So is it the same thing? Is it similar? Or?
I mean, yeah. Typically in the literature, this is sometimes called the instantaneous regret. I mean, instantaneous in the sense that you don't have accumulation over time of something, right? In online, I mean, regret is typically appears in online analysis, where you have something over time and you want to compete with some predictor which is the best in the hindsight over time, right?
But here we don't have any action. Like there is no action space, right? In principle,
I mean,
we can
the action
introduce...
space is a space of distributions, right?
Okay.
So it would be like if you think in online, in case of online, if you think about prediction with experts' advice, or like hedge algorithm, it's also playing in the space of distributions. I mean over actions, but here it's over some strategies or whatnot, right?
Okay, thanks.
Yeah.
More questions? I have one. At the beginning, you mentioned you need to basically you want to have a black box approach, so you don't want to look into the model. But so what you get then is a sample, but you also wanted to have a likelihood with it. So basically, you need to see the token probabilities for each token coming out, right?
Yes.
But you don't need the rest of the token distribution, do you? at any point. So you only need to see the probability for the token that actually was generated.
Yes, I mean technically you just need a log likelihood for the entire
the whole,
generation,
yeah.
right? And you can construct, of course, that it's just a sum of log
Yes.
likelihood tokens, right?
But can you make use of actually I mean, if you actually do know all the probability distribution across all tokens, can you make use of that to I don't know, get a better bound? So the insight could be that maybe, I mean, if we think about hallucinations, if you see that there are some other alternatives that were not picked but were still relatively high probability, that and if there is one, or if particularly, or if it's all spread, maybe that makes a difference, and maybe somehow it can be used to get a better bound.
So you're asking basically if you would know distribution over tokens ahead of time and could query what's the probability of any token, right? Mm-hmm. Yeah, then you could directly, I mean, given the some set of responses, I mean, you would come up with responses in some way, I suppose, right? Either sample them from the model, or maybe have a sample of responses. You would be able to directly estimate mutual information because now you have access to the joint distribution.
Right. Yes, but what I meant is that, I mean, because your maybe produced text is relatively long, and so you don't get a full distribution out, but for each token in your sequence you do get this alternative probabilities, or probabilities for all alternatives, but it's not branching out the whole tree, but just at every point you have that token probability distribution. So can you still, I mean, for example, practically, if I'm using an LLM, and even though I'm doing just one generation, I do get more information than just the likelihood of that sequence, but I can observe the moment of generation. At least if I'm running it in my computer, then I do see the full distributions at every generative moment.
I see what you mean. I guess I don't know would be the quick answer, but somehow, yeah, I'm not sure you can leverage this in some way. At least not in the in the context of this result, because the fact that you observe this, so maybe what you're talking about, whether it's possible to construct additional trajectories, because you're saying that at any point at any token you see additional probabilities, and you can construct additional trajectories there.
I mean, you don't see the full trajectory, but you see that there could have been a trajectory starting from this point, which might have been also quite likely, but we didn't follow on that, so we don't know the rest of the trajectory.
Right, we don't know, right? So there is insufficient information somehow, right? Mm.
As a follow-up to Meelis, maybe that can be derived from the beam search result. I mean, you have to track parallel trajectories all at the same time. But I'm not sure. My actual question is, you started with this iterative prompting, and that the definition and the theorem is based on that. However, I think intuitively, if you do non-iterative reprompting, you just sample the response, I don't know, 1,000 or n times. Even then, intuitively, it seems the same conclusion, that if the mutual information is very high, so that answers are diverse, that means a very unreliable model. So do we need the iterative prompting here? Or is it only for, for deriving the definition?
I see what I mean. So somehow this theorem holds for any n, and that's what you're talking about, I guess. And what if n is 1?
Not even one, but I mean, so here in order to generate y number n, we have to first generate y n minus 1.
Oh, I see.
Right? Because you proposed iterative prompting, like you reprompt, and again, given the previous responses.
Right.
But
this is
it's
exactly
faster, or it can be done in parallel. We just ask for n independent responses. And if those are different, that already intuitively tells us that the model is unreliable. And that can be done, that can be optimized, I think, further than iterative prompting.
But then, in that way, since you are not doing it iteratively, you're not really sampling from a joint distribution, right? Or unless you make an assumption that it factorizes.
Like a naive assumption
right.
that
In
they are
that case,
independent?
there is not much to do, right? Because this is going to be 0.
Okay, because all of this is based on your previous claim or theorem that a good or what was it, a well-defined language for any kind of n, it will converge to just an independent.
Right, but that's.
And this estimates the level of digression from that good language.
So if there are dependencies between y's here, then clearly this is going to be somewhat far from the independent. Remember, the intuition is that this holds. In fact, if I replace q by any other distribution over n responses, joint this distribution, then this bound holds for any distribution, right? Because what it tells is that no distribution can be close to p. Close to p that satisfies independence assumption if there are dependencies between random variables, right? So it's kind of a so it's a uniform result in a sense that q can be anything here, but it's just a convenient way to look at the if you choose it to be this joint distribution of responses.
Okay, nice. It can be used offline, even if it's expensive, maybe to, I don't know, generate reliable data. Or we can pre-compute some prompts where the model remembers, like we just remember the bad prompts and just tells, please don't ask me that because here I don't know.
Right. Or like if you want to identify which prompts are genuinely hard, right? Or something like that.
Yeah, and what in my opinion is elegant that is on the right-hand side, there is no dependence on P whatsoever. I mean, it's only the Q, so it doesn't depend on the ground truth. I mean, that's of course what we need in practice, otherwise we couldn't do anything, right? So, yeah, it's nice that this theoretical result exists. Okay, but I'm afraid we have run out of time, so thank you very much, Ilja.
Thank you for inviting us. Yes. Yeah. Oh, thanks. Yeah.